Good morning. So, I welcome you all for the last day first session. So, today we do not have much technical thing, but you have to write exam at the end, and then we will conclude with a proper validity session, okay, where we will distribute your certificates, and maybe I request you to speak something about the event as a feedback. Okay. So, let us start my presentation. So, today I will be speaking about solar collector testing and quality control, because in last 4 days what you have got the information about its fundamental and its various applications, and not only for only hot water generation, for hot air generation, and then for electricity generation. Also you have learned many things on design perspectives, like how a pumping stations can be designed, how we can design a off grid system. Of course, and today you will learn about design of a grid connected PV system, which will be taught by Professor Christophe in the next session. So, here in this presentation, mostly what I have covered is about the testing procedure for a liquid flat plate collector and a solar air heater, and then also few things I have included about drying of agricultural products. So, let us see how we can move ahead. So, this is the outline what I have listed for this presentation. The need of testing, why this testing is required, and then how this testing is performed in liquid fat plate collector as well as solar air heater, and drying kinetics and drying calculations. So, this drying calculation section I have shifted to this tutorial part, then we will do the calculations, and then you also help me in involving in the process of doing the calculations. And then finally, some of the aspects of quality and standards of FPC components, because see, until and unless you have a proper quality control, you cannot actually tell the efficiency of the plant and then its quality. What I mean, like suppose if we do not have this kind of standards, then any of the manufacturers can manufacture, right. So, people will not be having any range of parameters to control the quality. So, what will be the transmissivity? So, that has to be standard. So, if the extinction coefficient is about 4, so of course, your thing will be very, very transparent, and your quality will be very, very good. So, someone has to certify it. So, I have attended one very important meeting in MNRA, and that the meeting was exclusively on quality control on solar flat plate collectors, because see, we need the flat plate collectors in everywhere, because it's a such a nice technology, because you just install the device on your rooftop and you will get the hot water. You do not have to turn on the system which consumes electricity for generation of hot water, right. So, in Bangalore, if you see, in most of the household they are having liquid flat plate collector, and then there was a blackout in Bangalore, and then that was happened in the morning, and people have done a lot of research and finally found that this is due to use of greasers for hot water generation. Okay. Then this government took this matter very seriously, and they said every household you must have a solar water heater. If you could not produce the certificate that you have a these installations, then you will be not getting a lot of things from the government. Okay. So, this is very interesting, that is why it is very, very important. So, now before I start that testing process, you already know the different applications. This again I am reiterating it. What are the primary applications of this liquid flat plate collector? It may be for generation of hot water to meet the demands in the indoor swimming pools. Okay. Then the water heating in domestic applications. Then milk pasteurization is also very, very important. We need hot water. Then power generation, and of course at low temperature power generation. Then drying, solar water heater for biogas. Okay. So why I have written solar water heater for biogas? If you see, say let us consider this northeastern states of the country, and if we consider summer and then winter. Winter in our place, it goes temperature reported minimum is about 13 degrees Celsius, and there are some places like Arunachal or maybe in Meghalaya, it goes sub-zero sometimes. Okay. So what happens, this microbes what is inside the biogas plant, which is responsible for generation of biogas, they could not sustain at that temperature. So we need to maintain the temperature about 30-35. It works best when the temperature of the digester is about 35, which is called mesophilic temperature range. Okay. So if this temperature goes down, we need some kind of auxiliary heating. Okay. So from where we can heat it? Can we install a solar collector and then use a heat exchanger which can be installed at the digester, and then you heat exchange it, and then that heat exchange that the heat transfer fluid can be circulated again, and this will maintain the temperature so that these microbes cannot die out, and they could not suffer in thermal stress. Okay. So that is how I wrote this solar water heater could be used for biogas generation or maximization of biogas production rate. And slurry drying. So biogas plant, you have inlet tank, and then you have fermentation chamber, and then outlet tank. So from the outlet tank you can take the slurry out, and you can apply in the paddy field or maybe in the vegetable gardens or maybe in the flower gardens, right. It is very good nutrients level. So can we make some kind of dried cake which can be sellable, and for that condition we can use this drying, solar drying. Okay. So these are just some of the additional applications of liquid flat plate collector, and what I am showing here, how we can maintain the temperature in swimming pool. So we have collectors, it is arrays, not only single collector, there are many collectors which are connected in series or parallel, and then you need pumping systems, then filters, and then you regulate the amount of water required to heat exchange to maintain that particular temperature needed for swimming pool, right. Also you have seen the use of FPC for power generation, right. So what you can see here, it is a solar flat plate collector, it is arrays of solar flat plate collector, and you raise the temperature, and I am saying a simple liquid flat plate collector which can deliver a temperature at 100 degrees Celsius, right. Then your storage is at 100 degrees, maybe 100 degrees Celsius, and you can use the intermediate fluid or maybe that other fluid like organic fluid which can be bring back to this liquid part, which is nothing but storage, and then exchange the heat. Okay. And you identify a fluid which will evaporate at low temperature like ammonia or other refrigerant. Okay. Then what happens, that can be expanded in the turbine, and then you condense it and then use a pump to circulate. So we have three different fluids. In the first case we have maybe glycol or maybe water, or maybe in between you can have another secondary fluid, and then you will have tertiary fluid, or we can actually reduce this secondary part. So we can have only two fluids if we remove these purple colored lines or heat exchanger, right. So here it is very easy to find out the Carnot cycle efficiency, right. It is eta Carnot is something like 1 minus T2 by T1, right. So T2 is what is your outlet, and T1 is the inlet temperature. So you can find out. So if you do these calculations, the efficiency of this kind of system is very low. So, as you go on increase the inlet fluid temperature to the turbine, then what happens, you can maximize the Carnot cycle efficiency. So, that is how we are getting very low Carnot cycle efficiency here. Okay. But what you need to do for this kind of management, you need to have different kind of working fluid. Okay. It is an organic fluid. So, it may be R11, R113 or maybe R114 or that kind of fluid having lower boiling point. Now, why this standards testing is required is of course the for comparing the efficiency of different types of collectors, okay, and an essential basis for their selection for a given application as well as their design improvement. Okay. So, once we set up this testing rig, then we can say okay, these are the parameters which influences the performance of the flat plate collector. So, what could be the design perspective? Can we increase or decrease the transmissivity? Can we increase or decrease the inlet fluid temperature? Can we increase or decrease the mass flow rate, and what mass flow rate it will work? But in case of liquid flat plate collector, since the liquid side heat transfer coefficient is more, then we do not have to perform the experiment at different mass flow rates. So, single mass flow rates will give you the entire characteristics of the collector system. Okay. But in case of solar air heater, since it is air, its heat transfer coefficient is very low, then we need to perform the experiments at different mass flow rates. Okay. So, what are the essential requirements for this testing? We need an arrangement for inlet fluid at constant temperature with flexibility to set different values of inlet temperature. So, so that we can control the temperatures, and you can see what will happen if we change the temperature inlet. Okay. And then pyranometer we need to measure this watt per meter square, or what is called global radiation and diffuse radiation. Then provision for recording mass flow rate and different temperatures. That means we need mass flow meter and thermocouples, thermocouples. So, we can that means it is a temperature sensor. So, we call it as temperature sensor, and equipment for measuring pressure and pressure drop across the flat plate collector. Now, if you see, this is the arrangement we normally do for outdoor flat plate collector testing. So, what you could see that the first part, this is the flat plate collector, what you have purchased for testing, and then we have flow meters, we have pumps, then bypass valve. I will explain the function of each and every component used for this testing purposes. And this red colored rectangle is quite interesting. We need cooling water and a heat exchanger and a storage tank, and sometimes if we could not provide the sufficient temperatures, we need an electrical heater. So, this component actually very important, as mentioned here. This controls the fluid inlet temperature and fluid flow. Okay. So, that is how the combination of heat exchanger and the storage tank with an electric heater provides a means of for adjusting and controlling the inlet fluid temperature to the collector to desired values, right. Here what happens, we need to perform the experiment at desired temperature and mass flow rate. Okay. That is how the function of bypass valve. So, here what happens, if we have to perform at certain mass flow rate, say maybe M1 kg per hour, that is a mass flow rate. So, if we have to control, what happens, this is the way or piping system through which fluid flows, and we can monitor the flow rate by using this flow meter. If that already calculated mass flow rate could not be controlled, then it will be difficult. So, for controlling purpose, we can use this bypass valve, and we can fix it what mass flow rate is. You have already set to pass through in the flat plate collector. Okay. And this part is for heat exchangers, right. There are many difficult situations, there are number of test processes. So, what test process we are going to explain is under steady state condition. So, what will happen under steady state condition? So, the standard testing standard specifies that the collector shall be tested under clear sky conditions to determine its efficiency characteristics. Okay. So, if your climate is not favoring you, that means there is no clear sky, then what you will do? It is very difficult, because normally these experiments are performed on a clear day and during the midday, or when sun is on your zenith. Okay. It starts at 11:30, then you take 4 readings till 1:30. So, at least 4 set of readings you can take, and that has to be continued for 4 days. So, minimum 16 set of data is required to characterize a flat plate collector. Okay. And that too you are making at different mass flow rates and inlet fluid temperature, right. Now, condition is, suppose you do not have clear day and cloud is covered, okay, only hardly you will get 2-3 hours time, then how you will perform the experiments? It is very difficult, right. So, that is how people are doing transient analysis by noting this delta t. So, at certain period of time how delta t is changing, and from that they are configuring, that could be the profile, because we need to perform it. So, here the kind of test we are going to explain, it is under steady state condition, but in case of when there is very limited solar radiation, but still you want to perform the characteristics of a flat plate collector, you will go for transient analysis. Okay. So, this is very important. So, what are data you are going to record? It is mass flow rate and TFI. So, these two you are going to fix it, and then other things you are going to record, right. What will be the fluid outlet temperature, okay, and then other parameters. And you need to measure flow rate, then outlet inlet temperature, solar radiation, ambient temperature, and wind speed, right. So, that is how I said you need to start experiments at approximately 11 o'clock, and then you finish by 1 o'clock, okay, that is the solar noon. So, that time you consider and do the experiments, and during this test under steady state condition, so any bias due to transient conditions is eliminated. Okay. Also, you can see what are the conditions while testing the solar flat plate collector. So, solar radiation should be always more than 600 watt per meter square, even though we can write it is suggested 700, but if it is more than 600 is fine. Okay. And what could be the global radiation variation? Normally what happens, we prefer to conduct this, but this solar radiation is varies, okay, and 1 hour time we consider it a like under steady state condition, right. So, we consider if the variation is plus minus 50, then we can perform the experiments. Okay. Then ambient temperature, it should be plus minus 1 degree Celsius, then flow rate maybe plus minus 1%, fluid inlet temperature maybe 0.1 degree Celsius, and then temperature rise across the collector is plus minus 0.1 degree Celsius. That much of variation is all right for doing the experiments, and also we need to check the wind speed. What should be the wind speed? If wind speed is very high, then we are not suggesting, because what happen if wind speed is very high, then you are actually promoting more heat transfer. So, that is also not suggested, because these sets of experiments were performed by many researchers, and after doing so many calculations and research, they have concluded. So, this range is sufficient to characterize a flat plate collector, right. And of course, mass flow rate you can see 0.02 kg per second per square meter of gross collector area. Okay. That's the condition or constraint you can say for designing a liquid flat plate collector. Now, as I have explained in the first class, like why to develop this Hotel-Wheeler-Bliss equation, and earlier when we defined QU, which is nothing but useful heat gain, right. So, useful heat gain, how we have calculated, you remember, right. So, once you know the amount of solar which is absorbed by the absorber plate, and then losses taking place from the top, sides and the bottoms. then we can perform what is no QU, right, very easily you can calculate, right. We have solved that long problem in trial and error method what we have solved. So, once we know that, then we can find out, but our approach is, can we express this useful heat gain in terms of fluid inlet temperature. So, while doing so, we have developed this expression called Hotel-Wheeler-Bliss equation. QU is Fr multiplied by AP, which is the plate area, and then S is the amount of flux received by the absorber plate, then UL TFI minus TA, right. So, if we divide this expression by AC by IT, this is the collector area, because in case of collector system we can define the efficiency in terms of maybe gross collector area or maybe plate area. So, both are possible. Okay. So, what we have expressed first, this expression in terms of collector gross area. So, QU is known to us, this is MCP TFO minus TFI, that means difference between the outlet fluid temperature and inlet fluid temperature, okay, and mass of the water which is circulated, and Cp is the specific heat of water, and AC is the collector gross area, and IT is the amount of radiation which is falling on the collector system, not in the absorber, right. Now, we know this expression, and this is very useful expression, and if we divide this expression by AC multiplied by IT, then you will have this expression, right. Now, this is nothing but your instantaneous efficiency, what we have defined before, right, and this is nothing but this expression by S into IT, and then this is divided by IT. So, you have IT at the bottom, because AC is out from the entire expression, and also we know this S, the amount of radiation flux received by the absorber, is nothing but the amount of radiation flux which is falling on the glass cover or maybe collector system multiplied by tau alpha average. So, it takes care of both diffuse and normal radiation, right. So, we can write it like average tau alpha values, because in our previous lecture we say it is a classified way of doing the calculations. Okay. So, if we know this tau average, we can multiply some parameters, then we can find it out. Okay. So, this S can be expressed in terms of IT and tau alpha average, and if we substitute this expression, we will get an expression of this kind, okay, tau alpha, and then you will this expression. Now, if you look it very precisely, it will be something like a straight line equation, okay, because these all are constant for a particular collector. AP is constant, AC is area, and this is Fr is constant. Already this is the resistance of Fr, but the heat flows from the collector system to the fluid. Okay. So, how much radiation actually is not allowing to go there, actually it is like a resistance, thermal resistance, and this is the overall loss. Okay. So, that means this part, if you multiply with this is like a y is equal to mx plus c or minus c. Okay. Here what you can see is a minus c. So, it is like a straight line equations having the slope of this part, and this is the this is intercept, sorry, this is slope. Okay. That means this is y, this is m, this is x, and this is c. If we define something like y is equal to mx plus c. Okay. So, this is like c minus m into x if it is y, if we define as y. Okay. So, we can actually make something like this. So, this equation comes from some kind of experimental commercially available collector systems, and they found that this is something like this. Okay. So, if we plot it, so you can next slide you can see how we can develop the plot, and we can find out these m and c values. So, this kind of expressions you will get finally. So, that means if we plot efficiency and you have this parameter, then you will get a straight line, and that is a negative straight line. Okay. So, you will get something like this. Of course, you will get a lot of scattered data, and you need to fit the straight line, and you can develop an expression. So, finally, you will get this kind of expressions for a collector. AP by AC is 0.99. Already you know this plate AC is about 1.2 times AP. Okay. So, this kind of assumptions also you can make. Normally, it is 1.2 times more than the observer area, and this parameter is about 0.909, and then we can find out FR tau alpha average is how much and FR UL is how much. So, in certain cases, if we consider AP and AC are same, maybe we can express this instantaneous efficiency in terms of plate area. Then what happens in the earlier expression, what we said, this will be 1. So, you do not have to think much, and then its complexity somewhat reduces, and you can find out. So, once you know this, then you can develop this kind of expressions, and then it is very easy to find the efficiency at certain conditions when you know the fluid inlet temperature, ambient temperature, and then radiation. Okay? Because at the particular time, you must know what is the intensity of radiation, then fluid inlet temperature and ambient temperature. Okay? So, then you can plot this TF5, and what equation what you get, this is a commercially available solar collector. And this collector is having a gross area is 2.27 square meter and mass flow rate of 0.0456 kg per second. Okay? So, you can get this kind of expression, right. Now, so as I said before, for liquid flat plate collector, so why single mass flow rate is sufficient to characterize a flat plate collector? Because change in mass flow rate do not appreciably affect the performance, because the relatively high values of liquid size heat transfer coefficient. This is very fundamental. So, once you could answer, then it is fine. So, this is because of the liquid side heat transfer coefficient. And for this reason, although the efficiency curve of a collector is determined for a particular values of mass flow rate, it can also be used for predicting the behavior of the collector for other mass flow rates, which differ a little from the values used during the test. Okay. So, it is clear to you, right, why actually we single mass flow rate is sufficient for characterizing a flat plate collector. And if we talk about the performance over a day, so what actually we are getting, it is something like this, and we really want this kind of pattern, right. So, it will be something like this kind of pattern. So, if we plot it, then you will have this kind of informations on a clear sky, and this kind of information or this kind of data is important when characterizing a flat plate collector, and of course, this kind of weather is required for doing the characterization. Okay. Now, if I take an example of this kind, say a liquid flat plate collector has the following characteristics parameter. So, FR tau alpha average is given and FR UL is given to you, and it is operating under the following conditions. Solar flux incident on the collector is known, and then water flow rate is known, and it is 0.015 kg second meter square of the observer area. Ambient temperature is known, inlet temperature is also known to us. We need to calculate the mean absorber plate temperature of the collector if the collector efficiency factor is 0.9. Okay. And interestingly, if the circulating pump fails, what is the maximum temperature attained by the plate? So, in the last session, Professor Christophe has already explained what happens. Suppose if you are going for during the weekends, then what kind of measures to be taken, right, for say household flat plate collector. First thing, you can cover the flat plate collector. Second thing, you can release the water and open the valve to release the hot water. Okay. So, now my question is, what maximum temperature you could achieve under that condition. So, if you left for during the weekend and you have forgotten to turn off the system, then what could be the maximum temperature on that day. So, it is related to the last discussion held. So, can you process? I have given those equations required to solve this problem. So, what is QU for Hotel Wheeler Bliss equations, and then in terms of mean plate temperature and then FR values. Can you tell me some of the things, like I will just help you. So, we know the instantaneous efficiency, which is FR tau alpha average minus FR UL, then you have TFI minus TA, then you have IT. Okay. So, what is this value? FR tau alpha average is 0.68 minus FR UL is 6.1, and what is this value here? TFI minus TA is 40 minus 20 is 20, and what is the solar radiation? It is 900 watt per meter square, right. So, you will get a value, you can cross verify it, it is about 0.544, that means 54.4 percentage. Okay. And also you know, instantaneous efficiency, which is defined as MCP, then you have TFO minus TFI, and you have in terms of plate gross area, and you will have IT. Okay. So, here mass flow rate kg per second per meter square of the observer area is given. So, that means this area is this information is given to you. Okay. So, this information is something like 0.01 kg meter square second square meter square, okay, second meter square, and you substitute this IT and CP values, then you can find out what is the instantaneous efficiency here. So, instantaneous efficiency is also known to us 0.544. Then what else you can TFO, right? So, TFO you can find out. So, as per my calculations, it is 47.8 degrees Celsius. Okay. So, you know these expressions for FR expressions are known to you, and collector efficiency factor is 0.9, is FR is given to you, right. FR is given to you, and also you can do something on so here FR UL is 6.1. So, you can find out UL here is UL will be your 6.1 by F of R. Okay. This is also one expression, so you can use it, and FR tau alpha, and from the other expression from here there is tau alpha average will be 0.68 divided by f of r. Okay. So, how will you find out f r values? F this is given actually, no. If the collector efficiency factor, this value is nothing but 0.9. Okay. So, we need f r. Can you do some kind of adjustment? So, anyway these values are known to us. Okay. And that means, and this is also known to us. Okay. So, if we could express UL in terms of FR, then I think we can do it. So, can we express UL in terms of FR? So, UL is 6.1 by FR. So, if you substitute that, UL is equal to 6.1 by F of R, then actually we can find out. So, that means FR is equal to, then you have UL is 6.1 by FR. So, this FR will be here, and then you have 6.1, and this value is known. This value is 0.015. Okay. Sorry.
Below UL.
Yeah.
That can be put in the next slide.
Yeah.
For UL value are already given.
Yeah. This FR will FR goes off. Only one FR will be here. Yeah. So, from here you can find out what is FR. So, I am not going to write the things. So, from here what you will get, FR is equal to 0.83. So, which is in the range what we have explained before. So, once we know FR, then we can find out what is UL. It is 6.1 by 0.83. So, this is 6.1 by 0.83. Then you can find out what is UL, right. So, everything is known here now. FR is known, then we have UL is known. Okay. Then S is IT by tau alpha average, which is also known, because tau alpha average is 6.8 divided by f of r. F of r is known. Okay. So, everything is known. So, we can find out what is QU, and then once we know this QU from here, then we can substitute here and we can find out what is TPM. So, plate temperature we can find out once you know QU, and that is known from this expression. Okay. So, this Q or maybe what I can say here, QU by AP, you will get a value of about 498.01 watt per meter square. And if you substitute here and do the arrangement, then from here you can get TPM is equal to 50. It is 53.8 degrees Celsius. So, this observer plate temperature of the collector, we have done it. Okay. So, this problem is very important as far as exam is concerned. Okay. So, TPM we can find out it is 53.8 degree Celsius, right. And what could be the second part of this problem? If the circulation pump fails, or maybe you have forgotten to turn off the system, then what could be the maximum temperature of the collector or maybe fluid. So, as you know, if the temperature increases, that may damage many of the components of the collector system, right. So, what will happen? That means you are not collecting QEV 0. If QEV 0, you are not collecting the useful heat gain, then what will happen? This part is 0, then this is equal to this, that means S is equal to AP, that means what? S is equal to UL TPM minus TA. This TPM will be how much? You can very easily calculate, right. So, circulation pump fail means you are not using the useful heat what you have generated, that means QEV is equal to 0, and then you can maximize the temperature, or if you know what is the design temperature or stagnation temperature. Okay. So, as per my calculations, it is about 120 degrees Celsius, close to or approximately, no, for this approximately 120 degrees Celsius. You can see here TPM we got 47.8, but when you are not collecting, temperature rose up to 120 degrees Celsius. Okay. So, it is really significant, right. So, this kind of things are very essential to consider as far as flat plate collector is concerned. Okay. Fine. So, I will move to the next slide. You got it, right? Problem is understood. So, few data are given, you have rearranged the data to find out this QU. So, once you know QU, then you can find out what is the plate temperature, and then if circulation pump fails, that means you have forgotten to turn off the system, then your temperature might rise to a very high values. Okay. So, that is nothing but your stagnation temperature. So, these are the calculations. So, now this testing of solar air heaters will study, and then some of the applications of solar air heaters in drying and electricity generations. So, here this solar air heater test procedure is almost same, but here since we have sensed the working fluid from liquid to air, then we need to perform the test at different mass flow rates. Okay. So, we need components like the solar air heater, a blower. So, we need to blow the air here, and earlier case we use pumps. Okay. So, that was liquid, and an apparatus for conditioning the air, which ensures that the air enters the air heater at the desired temperature. So, inlet temperature has to be fixed. Okay. So, that is how this reconditioning apparatus will be there, something like heating, sometime heating with heat exchangers. If it is not sufficient by the solar radiations, then we need to recondition it. Okay. Then we need to supply, and there is a mass flow meter, orifice meter. Okay, that is used for, or maybe sometimes other arrangements can also be suggested for measurement of air, and that regulated flow will flow through this blower, because blower will act on it, and then it goes through this solar air heaters. It may be single pass solar air heater, or maybe double pass solar air heater. That depends the kind of solar air heater you are using, or it may be air heater with fins, or maybe some other arrangement, or maybe it's a PVT system. Okay. If there is a PV cells, and then you have absorber, and then you can blow air under the absorber. Okay. So, you can fix it here. Interestingly, you can see there are many thermocouples attached here before entering to the air entering to the system, and also there are mixing vents, because it's air. So, there will be non-homogeneous temperature, right. At different positions temperature will be different. So, in order to uniform or uniformly measure the temperature. So, this kind of vanes are attached, and then finally, what we are measuring is the fluid outlet temperature, and that too not only single thermocouples, we are averaging the temperature, okay, because temperature will be different. It is not liquid, it is not no molecules are dispersed, it is not very closely packed. So, the temperature measure at different locations will be different, it is not constant, right? But we need to take the average of the temperature. And this delta P for solar air heater, pressure drop is very essential, okay. And we have discussed in the very beginning class that what are different arrangements we can make. We can use some kind of what is called matrix to increase the heat transfer coefficient, okay. But at the same time we are actually increasing pressure drop, right. So, pressure drop in this case is very essential, okay. Even though there are certain arrangement which actually augment the heat transfer process, but it might reduce the pressure drop or maybe increase the pressure drop or maybe increase the power required to blow the air is very significant or very high, right. So, we need to decide what arrangement will be best, and that is how we need to know what is the delta P here, and this is the manometer. So, we can find out what is delta P, and from that we can find out really what is the pumping power, which is already explained by Professor Christoph in his one of the classes, like in friction factor. And then if you increase the roughness, then what will happen? What is the value of friction factor for this kind of conditions, and then accordingly what could be the delta P values, and that means pumping power, okay. So, this measurement techniques you must know very precisely, and also why this kind of arrangements are made and what benefit you are going to get. This is very important, okay. And then we can do the experiments at the different mass flow rates, and we can find out this characteristics curve, and then we do the analysis and characterization. So, you will get this kind of scatter data, and again we need to have different fitting coefficients and generate some kind of plots and then equations to relate this instantaneous efficiency and this parameter here. So, earlier things were different here, and here what happens, we are using this mean temperature, okay. TF bar, it is a mean temperature of the fluid, and then minus TA, then IT. So, this parameter we need to investigate to find this efficiency, okay. We have a very interesting problem which I will solve now. So, this is quite interesting problem. So, efficiency curves shown in this figure are obtained for a solar air heater of dimension L1 is 1.2 meter and L2 is 0.9 meter, that is a dimension, which is tested under a range of flow rates varying from 25 to 200 kg per hour, okay. So, different flow rates, okay, because of heat transfer coefficient, and we need to find the efficiency which would obtain and the corresponding mass flow rate if the air heater is used under the following conditions. So, air inlet temperature is 54 and outlet temperature is 74, ambient is 26, and solar flux incident on the glass cover or through the glass cover is 950 watt per meter square. So, how to proceed with this? So, characteristics curve is something like this. It is TF bar minus TA divided by IT, and this is the unit of this parameter, and this is the instantaneous efficiency, and this what you can see at different mass flow rates, characteristics are something like this, okay. So, we need to find out now efficiency and the corresponding mass flow rate, that means the optimized mass flow rate, and we need to rely on trial and error method. So, can we initiate like now values are given to us, and as I said, TF bar is nothing but you have average fluid temperature, and this is like, if you know, this is average fluid temperature. I will write average fluid temperature, and this is something like TFO plus TFI by 2. Okay. So, fluid inlet temperature, outlet temperature is known to us. Then what could be this TF bar? It is 64. So, once we know TF bar, then we can find out this parameter TF bar minus TA divided by IT, right. So, IT is also known to us, it is 950, this is the IT values, and this is 64. What is the ambient temperature? Is 26, right, and IT is 950 watt per meter square. So, if you substitute, then what value will get? 0.0. But here what I is a kilowatt. So, kilowatt means it's fine. So, then what you will get? It's 40. So, your unit will be meter square kilowatt, right. So, unit is kilowatt, that is why I use kilo, and that means this is something like your 0.95 kilowatt per meter square. Okay. So, then if you know this parameter 40, so this is 40, okay, and you go up here 40, and this is the point, and this is actually 25 kg per hour mass flow rate, and you find out what is the corresponding efficiency. Okay. So, this is the corresponding efficiency. So, if center is 25 here, it is less than 25. So, to be precise, as per my calculation, if we assume, okay, if we assume m dot is 25 kg per hour, then efficiency will be at this value, it is 24.2 percentage. So, 24.2 percentage. Okay. So, if this is the value, then can we find out what is QU, because we know this is equal to QU by IT into A. Okay. So, this is, or it may be, this area is given to us. So, if you go back from here, what is the area? 1.2 multiplied by 0.9 is the area, and efficiency is known, then you can find out what is QU in this case. QU we can find out, this is 0.242, then you have 950 and area 1.2 into 0.9. Okay. You can find out what is this value. 248. 248. What is the unit? What? It is what? Is what? It's fine. So, 248 you got, and then we know QU is equal to mCp delta T, and it is 248. And Cp of air, maybe you can consider like 1007, that means 1.007. Okay. So, Cp of air 1.007 into 10 cube, or maybe kilojoule or joule per kg. Kelvin or degree Celsius. So, you can find out what is m. So, I want in kg per hour. 248 Cp is 1.007 into 10 cube. Okay. And then you will have delta T. What is delta T here? What is the value of delta T? 74 minus 54, it is 20, and then here it is 3600, because I want in kg per hour. So, what is the m that value? 44 point. Kg per hour. See, we have started with 25 kg per hour, but what we got is 44.32 kg per hour. So, our assumption is not valid. Okay. Now, again we need to go back and see what next we can do. Okay. So, it is 44.32. So, what we can do? We can get it say about 50 kg per hour. So, if I take 50 kg per hour, so the same line you go up, and this is for 50, and if we extend it something like this. Okay. So, this value we need to find out. So, precisely as per my calculation, it is about 28% efficiency at this condition. So, if we consider m dot is 50 kg per hour, then instantaneous efficiency is 50, sorry, it's not 50, is 28%. Okay. So, if this is the case, so can you tell me what is Q here? So, this is 0.28, then you have 950, then this area 1.2 multiplied by 0.9. Okay. So, what could be the value of Q? 287 watt, right? And then what could be the mass flow rate? Use the same process, then the mass flow rate will be how much? 287 multiplied by 3600 divided by 1.007, this is specific heat of air, then you will have 20. 51.35. So, we are somewhat close, right. So, now we can take this value and do the calculations, then you will find it is very close to these values. Okay. That means, we need to do trial and error till we get a very close values of 2 iterations. Okay. Then you can close the calculations and you can say that that is the final values. So, that is how we can do. See, we have seen at different mass flow rates, and initially we assume that it is 25 kg per hour, but this is not actually 25 kg per hour. So, then we have revised our assumptions, and we got a value which is close to 50, it is 51.35. Again we need to do one more time at this condition in order to strengthen our understanding that that is the correct values. Okay. So, once it is finalized, so if by taking these values you will get a value of somewhat like 51.5 again. If we take these values, then you will get 51.5. So, that means this is very close values. So, this is fine for us. Okay. So, you got it now why you need to do experiments at different mass flow rates. Okay. So, that is the basis of doing this calculation, right. Let us move to the next. So, now we will spend some time on solar drying of agricultural products. So, why do you need drying? So, in most of the times people approach us for solutions for effective drying. What drying process we can suggest and what could be the best drying methodology and device for meeting their demands. So, drying is required for many conditions, like say for example, if we talk about paddy, we need to dry, it is open sun dry only. So, there are a lot of losses taking place when you do open sun drying. Lot of insects will take, and then lot of when you collect this, lot of losses will be there. Of course, these losses are important for other animals or maybe birds. Okay. So, everything is required, but no, if these losses are very significant, then you need to take a measure. Okay. And also sometimes what happens, you have harvested the paddy and you need no drying, but season is not favoring you for drying because of rain and other climatic conditions. Then what could be the solution? Because you harvested for a long 4 months time, and then no you could not dry it, because of that no you are you cannot no spoil the entire paddy what you have harvested. So, we need a clear cut methodology to dry it. Not only paddy, say for example ginger or any other spices, maybe cardamom. You have got plenty of cardamom, plenty of gingers. Then how to preserve those? Because in as per report, many of the agricultural things as wastage because of improper drying and non availability of dryers. So, that is the basis of requirement of drying. And what happens, why this has not gained so much of popularity? Because this drying has to happen for a particular period of time, not throughout. Like a paddy, it harvested for a particular period of time, and rest of the time your dryer will be ideal. And then ginger will be harvested for a particular period of time, and for that period of time you need a sophisticated dryer, and rest of the year it will be ideal. Okay. So, can we have a drying methodology which will serve for all the spices, all the vegetables, or maybe all the other grains? Okay. That's the thing we should emphasize in order to have sustainability. Okay. And design of solar dryers are based on empirical and semi empirical data than its theoretical design in most of the cases what we see. And majority of the solar dryer designs are used mainly for drying various crops, either for family use or for small scale industrial production. Okay. Large scale things are not there as far as solar dryer is concerned. So, really it is a need of the hour, because agricultural things are increasing day by day, because population is increasing. We need more food, more spices. So, we need sophisticated and reliable drying systems. So, how this drying happens? So, drying means in the raw biomass it contains a lot of moisture, right. So, that the moisture has to be removed. Moisture means water. So, that is how large portion of energy consumed during drying is for transforming liquid water into vapor. So, it is latent heat need to be removed at atmospheric pressure, and water may be contained in various forms. It may be free water at the surface, or may be bound water which is inside the grains. So, it is very easy to remove the water which is above the surface, which is touching the surface, and there are some water which is inside the surface, it is very difficult. Okay. The free water is regarded as unbound, and the product is not hygroscopic, and bound moisture is trapped in closed capillaries, and the material is called hygroscopic. Okay. So, it is something like you need to provide energy and then evaporate, and particle will be dried, and your moisture will be out. And this hot air involves the simultaneous action of heat and mass transfer. So, here both heat and mass transfer will happen. So, heat is provided and mass transfer will take place. Okay. And also this moisture content can be expressed in either dry or wet basis. Okay. So, wet basis we represent something like mass of water to the sum of mass of water and mass of dry solids. Okay. And dry basis we consider mass of water to the mass of dry material. Okay. So, how this drying happens? Okay. So, here what you can see, we are representing this drying, that is dt by dx by dt, and which is running by mass per rate of drying, it may be kg per hour. So, and in the horizontal axis what you see, it is drying time. So, AB, what is AB here? AB is the time spent to heat up the material until the drying temperature is achieved. Okay. Then we will go for BC. BC is the constant rate drying. Then what happens? It will be constant. Drying is constant. Okay. And then this C and E is a falling rate drying, where a flow of moisture from mass interior is decreased continuously. Okay. And these things happens in majority of the grains and vegetables. And E, there is still moisture inside the product, and moisture removal takes place slowly by diffusion drying, that stops at D. Okay. So, that is how it stops. It goes moisture removes, then constant, then falling, then again it continues slowly because of diffusion, and it reaches at point D. And this is the drying characteristics for most of the grains. Okay. So, this is very interesting, and then when you are studying drying kinetics, the knowledge of this plot is very important, how really it happens, and then you can do some mathematics and you can find out the parameters. And water activity is also important for food preservations, as it is a measure and a criterion for microbes growth and probably toxin release of enzymatic and non-enzymatic browning development. So, this is very important, as you can see here mathematically we can express in terms of partial pressure of water solution to the partial pressure of pure water at the same temperature, and majority of the bacteria grows if this value of water activity is equal to 0.85, and mold and yeast grows at about the water activity of 0.61, and fungi grows at about less than 0.7. So, these values are very important as far as microbes growth in the substrate is concerned. So, for every food or any kind of agricultural products, there exists an activity limit below which microorganisms stop growing. Okay. So, that we need to find out. And also we must know what is equilibrium moisture content, which is defined as the moisture content when the vapor pressure exerted by the moisture products equals the vapor pressure of the nearby ambient air. So, it is related to vapor pressure. Okay. And also this is Swabson isotherm, knowledge is important, but there will be hysteresis. It is not always the same thing while absorption and desorption, there will be hysteresis, and this is also important. When you plot it water activity versus water content, then you can get this kind of plot. Okay. So, we will be solving a problem. Say for example, we consider grapes drying, and then we will calculate all the parameters, how much amount of energy and other things are required for drying certain quantity of material. And this as far as drying classifications are concerned, it may be active dryer or maybe passive dryer, that means natural circulations and forced circulation. You need to provide fan or maybe blower over the substrate in order to accelerate the process of drying. Then we will have direct and an indirect mode and maybe mixed mode. Okay. And direct is a box top dryer, indirect is a cabinet dryer, and mixed mode is like a tunnel dryer. So, people are doing a lot of mixed and then a hybrid drying system nowadays. So, we got a project recently, and that is on how to utilize biogas for drying purposes. So, biogas we are using and then purifying it, and then we have heat exchanger, and maybe at the top we have cooking, and then we will exchange the heat, and then we have a PCM storage, another heat exchanger where no PCM will be stored, so that we can extend the drying process. And why this kind of dryers are required? Because if you do not have solar also, solar radiation on certain periods of time, you can run the systems, or maybe at night times if you want, you can actually do the drying process. So, it is a greenhouse dryer plus heat exchangers. There are many heat exchangers, and then you will have what is called other reactor like anaerobic digester, from where you can produce some kind of fuel which is burned for increasing the heat. And this kind of cabinet dryer, you can see solar radiation is passing through these glass covers, and then this moisture from the vegetable and then grains will move up, and then drying happens and air is supplied from the bottom. And you can see this is forced circulation dryer. So, it is like direct grain. So, it is attached to the grain. So, air will be pumped through a blower, and it goes through this cover system, and then it is passed through this trays, and then finally this will blow out. Okay. Or maybe blower, sometimes you can attach it will suck the air. Okay. And that is how it is drying is done. And this is indirect grain forced circulation mode. We have blower and solar air heater is there over the solar air heater. That means maybe inside the solar air heater, hot air carries, and then it pass through this material. Feed will be here, and dry product will be collected here, and air will go out. And this is forced circulation. Already these kind of systems exist. And now one more very interesting thing you can see here as far as dryer is concerned. So, solar chimney power plant. So, what you can see here, this is a turbine, it is air turbine, okay, and these are transparent covers. It is like greenhouse. So, temperature maybe up to 20 degree you can rise, and then because of this density difference, it goes up and turbine rotates, and you can produce electricity out of it, and it is very tall. You can see here, this is like greenhouse, okay, and there is a gap, and it is a plenum. Air moves through this and then goes up, and air turbine should be placed in some of the locations here in the tower. Okay. So, here it happens. So, it consists of this central chimney, then greenhouse. So, these are a circular greenhouse, what you can see here, and of course, it is a transparent, and we need a very strong metal stand, so that it can hold the structure, and we need a fan and generator. So, it is a air turbine. So, it is a turbine will be there, and Dr. Mebratu, he has developed one compressed air energy storage systems. He also used the air turbine there. So, compressed air goes, and then it rotates this air turbine, and then generator is coupled. The similar kind of things. So, air moves up and rotates, and then there is generator. You can generate electricity. So, in Spain, you can see this kind of installations in desert place when you really require some kind of electricity, right. So, you do not have many options, but this kind of systems can be installed to get some kind of electricity out of these solar radiations. Okay, and just we need to define what technology will be suitable at that location. So, chimney is about 200 meter tall chimney and diameter is 10.3 meter. 10 meter is really big, right? So, it is 6 meter and then multiply with 2 and that many big, that is a diameter. Okay, and you can see this is the radius. Okay, it's a big one, and that's how many turbines can be installed in that pole. And solar collector area extended to a radius of 122 meter from the chimney, with glazing being 1.8 meter above the ground. So, this glazing are there. Okay, it is not open, this is glazing is placed, so that we can get more solar radiation, and area of the glazing about 46,000 square meter. It's really, you need a barren land. We cannot use our vegetable or visiting place, or what is called important place. Then there are 4 turbines of 5 meter long blades and rotates at 1500 rpm. So, 4 turbines are placed, not only single turbines, 4 turbines are placed in that place, and it produces 50 kilowatt of power. Okay. And this, of course, this energy conversion efficiency is very low, because temperature is very low, right. So, maximum conversion efficiency as calculated, it is found to be a function of height. As you increase the height, then you are expected to get higher conversion efficiency, and these all parameters are close to constant. Okay. So, TA and CP, how much TA will change? Not change much, because of course, it will be climate dependent, but it is a function of H. Okay. So, height of the chimney tower and temperature of the ambient air. Okay. So, can we just quickly solve this to get an idea about its efficiency? So, we assume that height of the chimney is 300 meter, solar collection area of the greenhouse is 50,000 square meter, specific heat of air is given to you, ambient temperature is known, and assuming the turbine generator set converts only 50% out of the maximum available energy into electrical energy, and the collection efficiency of the greenhouse is 25%. So, by considering this, can we calculate the maximum possible conversion efficiency by this chimney, and also the daily electrical output in a typical summer month having solar radiation 6.5 kilowatt hour per meter square. So, we need to also estimate the efficiency and then daily electrical output. Can you just tell me what is the maximum efficiency by using the expression? Eta max is GH by CPTA. So, height is 300 meter, Z is 9.8. and then Cp is 1005 and T ambient is in Kelvin in 305, right. So, it is, what is the percentage? 0.96 percentage. I think you have never seen this kind of percentage in life. It is 0.96 percentage, it's less than 1%. Okay. It is very inefficient, but we can generate some amount of energy. Okay. What could be the overall efficiency? It is 25% is the collection efficiency. Then we will have what is called maximum efficiency is known, and then we will have turbine generator set converts only 50% of the energy. So, overall is 0.0096 into 0.25 into 0.5, okay. Then multiplied by 100, it will be how much? .12, okay. So, how much is the daily electrical output of the plant? So, it is 6.5 kilowatt hour per meter square, and then you have collection area is 50,000. 50,000 is the collection area. So, overall efficiency is known. So, what really we want? Daily electrical output of the plant, daily electrical output of the plant. So, this is overall efficiency is equal to electrical, and then we have 6.5 kilowatt hour per meter square multiplied by, you will have 50,000. So, we can find out what is P. How much is the result? So, this is overall efficiency, okay, and then you want this electrical output. Output by input is efficiency, right? So, output is P, what we want, and input is solar radiation and area. So, in my calculations it is about 390 kilowatt hour, 390 kilowatt hour, okay. So, in there is a plant in Australia, its capacity about 200 kilowatt, 200 kilowatt, yes, 200 kilowatt, it's electrical, 200 kilowatt electrical, and it is 1 kilometer tall. It's 1 kilometer tall, and then about 7 kilometer diameter is the base. So, 7 kilometer is the diameter base, and then 1 kilometer tall, okay. It's interesting. Okay. Okay, then. So, these were some of the informations about solar air heater. Okay. Now, let us move to the standards for solar thermal collection collectors in the world. It is very briefly, I will just explain the standards because as I said before, standards are very important. Otherwise, there will be no restrictions, like everyone will produce and then you do not know about its longevity and other performance parameters. Then people will be complaining like this will not work, but this is not the case actually. If you set some kind of targets as far as quality is concerned, then everyone will be happy. Okay, but as professor said in one of the classes, like strength has to be something like this. He has used in the freeze, right, that he said about his experience to see the strength. It's really worked. It's very good strength. So that's also one important parameter. So quality control parameters, like we need to check the material quantity, like its glass cover, what could be the quality of the glass cover, okay, and what could be the material of construction for the glass cover, then absorber plate, okay, and then what are absorber coatings. So all the things need to be specified, okay, insulations, then thermal performance, it may be efficiency testing and stagnation temperature, which is very very important. I was repeating this. So these are very interesting thing, and then structural integrity. So leakage test is very very important. So if you are making something and the leakage is happening, then what will happen? So we need standards in all the aspects of the components and design, right? Say for example, if we talk about glass cover, as I said very briefly, what could be the extinction coefficient for your purpose? What is the strength of the glass cover? So these are very very important things. Then for coatings like selective coatings, what could be the absorptivity? What is the emissivity? So all the things should be very precisely written in the system, so that no people will be convinced like no, okay, longevity will be something like this. If it goes beyond the limit, then it will not work, and this is the appropriate range of working conditions. So all the information should be highly it should be written and then highlighted in the specification sheets. And efficiency is important, how much energy you will get at the end, and then thermal stress is important, because if hailstorm happens and broke every component, you are gone. And if it is a big plant, then all that money you have invested, it will be just no use. So at least some the strength has to be there to resist those shocks. And this ISO standards for flat plate collectors. So IS 12933-2003 is the standard for flat plate collectors. Still they are amending those what is called standards, because time to time we need to revise this, and that's how there is a big meeting, and Bureau of Indian Standards, they are actually looking into it to strengthen those norms, because you don't know from where these collectors are coming. It might be very low in quality and then other parameters. So this is important. So all evacuated tube solar water heating systems standards are there in 2016. Then all glass evacuated tubes water heating systems, we have standards of 16542. It is also formulated in 2016, and the source is MNRE website. And this is the standard, and you can see this all the components are very precisely mentioned for this IS 12933. What could be the quantity and what could be the strength, all the things are listed in the standards. Okay. And quality control test is a routine test we have, like static pressure leakage test is one of those, and external thermal shock test is also important, then thermal efficiency test. So these are primary things we need to concern about as far as quality control is concerned. So there should not be pressure drop, that means from that we can find out whether leakage is taking place or not. Okay. Then no appearance of swelling, then distortion or rupture in the riser and headers. Then as far as thermal shock is concerned, there should not be any crack or distortion, then condensation of water penetration inside the solar collectors. So once it is observed, then you can find out something is wrong. So we need to be concerned about it. Then for thermal efficiency test, this characterization confirms something like UR/UL has to be less than or equal to 5 watt meter square degree Celsius. This is one parameter. Second is like FR tau alpha average is greater than, it should be greater than or equal to 0.65. This is one of the important parameters as far as thermal efficiency test is concerned. And for BIS certification marking, these things has to be written on the device, who is manufacturing, its addresses, its serial number, then maximum working pressure in kilopascal or maybe some other units, values of these two parameters, FR UL and then FR tau alpha average. Then absorber material, surface coatings, what kind of surface coatings and what is the wavelength of absorption and emission, and then month and year of manufacturing and country of manufacture. This information has to be reported as far as the IS 12933 in 2003 is concerned. Then all glass cover evacuated tube solar water heating systems, you can see this IS 16544 2.16 is the standard time, and it's they say that exposure to solar radiations on plate of solar collectors has to be more than 4.5 kilowatt hour per meter square for 2 days. So that's the things, that means 2 days they have to perform the experiments, and after preconditioning of 2 days all parts shall be inspected by any visual signs, because it is like indoor experiments. So you cannot have constant 4.5 in outside, right? At night anyway it will be not there, and daytimes also it is varying. So there are some designs, confirmations and direct insertion of storage tank cell conforms to IS 16542. So these are all part of the quality control of IS 16544. So this is just the information. And also for storage water tank for all glass evacuated tube solar water heating systems, there are some general requirements, like outer clearing and outer sealing shall be smooth without any crack or obvious scratch, and no coating peeling off. So these are some of the general requirements, like sinking, and then maybe to avoid the entry of any foreign materials, and test requirements like capacity of storage tank shall be within plus minus 5% of 500 liters as per IS 16542 2016 is concerned. Okay. And for this we need to have the knowledge of measurement of solar storage water tank capacity, then leakage test, and then performance test. So primarily these tests are to be performed as per the standards, and then we can pass them if they qualify the minimum requirement. And there are different standards in different countries. You can see S396 they have procedure for testing of unglazed flat plate collectors, and then what is the minimum requirements for solar collectors, SRC standard 100, then 300, there are different standards. In China also they have different standards, and you can see in Brazil they have one standard, and European EN 12960 factory made solar thermal systems and components. Then South Africa they have the standards, then Canada they have set of standards. So they follow different standards, but no basic requirement is same, that the kind of test we have shown through 3 different conditions, leakage and pressure drop, and then efficiency or thermal test. And for New Zealand and Australia, the design construction of solar water heaters and heat pumps is one. Then Japan, solar thermal collectors, then test procedure, JISA 1425, then Korea, then Chile, then Middle East. So all the countries they have, and then this is very, very important as far as quality and standards is concerned. So with this I would like to conclude my speech, and in the second half we will continue that tutorial. We have 2-3 problems to be solved, and that will be like end of the session. So thank you very much. If you have any questions, then we can discuss. So thank you.